In this video, we will explore the bonding that occurs in organic compounds. The goals for this lesson are that you're able to describe the bonding that occurs in organic molecules, including trends in bond length and strength. Identify exceptions to the octet rule. Draw complete Lewis structures, including formal charge and resonance structures. Speaking of resonance structures, you should be able to identify major, minor, and equivalent resonance structures, and draw the curved arrows that relate to resonance structures of a given molecule. Let's get started. We will begin by revisiting this question. Are all organic compounds molecular? Are all inorganic compounds ionic? This question is relevant because it addresses the types of bonds in organic and inorganic compounds. So what do you think? Well, as we discussed in the last lesson, no, inorganic compounds can contain covalent bonds, such as carbon dioxide containing those covalent CO bonds. Inorganic compounds can also contain ionic bonds. So no, all inorganic compounds, and recall, inorganic compounds do not contain both carbon and hydrogen in significant amounts, while organic compounds do contain carbon and hydrogen in significant amounts. So no, inorganic compounds, again, can contain covalent or ionic bonds, and organic compounds can also contain molecular, well, they always contain at least a couple covalent bonds, and they can also have ionic bonds as well, so they can be ionized. So we see this example of a polyatomic ion. Yes, Gen Chem word. This polyatomic ion, that's an organic ion that you encountered in general chemistry. And if you did not encounter it in general chemistry, you certainly will encounter it in this class. All right, be sure you understand this before you move on. In order to show the bonding in organic compounds, we will need to, at a minimum, know the total number of valence electrons present in atoms and ions and molecules. And let's take a moment and make sure that we can count valence electrons, and why not, we'll also think about the complete electron configurations for these three atoms or ions. Please pause and try this. Let's compare answers. So for carbon, we look at the periodic table. We see that carbon has atomic number 6. Now, because it's not otherwise specified, we know this is a neutral atom of carbon. So that tells us that carbon has an equal number of protons and electrons because it is a neutral atom. So 6 total electrons. So 1s2, 2s2, 2p2. So that's 6 total electrons. Oxide. We have the O2 minus ion. Well, oxygen has atomic number 8. So a neutral atom has 8 total electrons. But this atom has a charge of negative, -2, so it must have 2 extra electrons. And so the electron configuration of oxide is 1s2, 2s2, 2p6 for a total of 10 electrons. Next up, the sodium cation. Sodium has an atomic number of 11. That means that every atom of sodium has 11 protons. A neutral atom will also have 11 electrons. However, this is an ion of sodium, has a positive charge, a +1 charge. That means that there is 1 fewer electron than protons. So this sodium ion has 10 electrons, so it has the same exact electron configuration of oxide. Why do these two ions that naturally form in nature, a little redundant, that form in nature, why do they have the same electron configuration? Yes, these atoms have the same electron configuration because atoms ionize to achieve a noble gas electron configuration, which corresponds to 8 valence electrons. The noble gases here in group 8A, with the exception of helium, all have 8 valence electrons, and all of them have a filled valence shell. This is a particularly stable arrangement of electrons. That's why atoms ionize and bond to covalently bond to achieve that arrangement of electrons. We call this the octet rule, that atoms bond either by making ionic bonds, transferring electrons, or by making covalent bonds, sharing electrons to achieve 8 valence electrons. Now, it is not the octet always, or the octet law. It is the octet rule. So we will encounter some exceptions to this. Speaking of valence electrons, let's go ahead and count the number of valence electrons for these atoms and ions here. So nitrogen, 5 valence electrons. Whoa, how does she know? She knows from the periodic table. It is your friend, right? Group number, the main group numbers, the A system. Those numbers correspond to the number of valence electrons in the neutral atom. Nitrogen is in group 5A, 5 valence electrons. Awesome. Now, what about the hydrogen cation? Yeah, well, a neutral atom of hydrogen would have 1 total electron, which would also be its valence electron. But this has a positive charge, so that means there's 1 proton and 0 electrons. So there's 0 valence electrons or electrons of any kind for the H plus ion. And we call this hydrogen ion, or simply a proton, because that's what it is. And you will encounter the hydrogen ion extensively in this class. Next, we have what is called hydride, or it's H minus. So hydrogen has 1 proton. If there's a minus charge, that means it must have 1 additional electron. And its electron configuration would be 1s2. So it has 2 valence electrons. And what about H2? Well, there's 2 atoms of hydrogen. Each one would have 1 valence electron, right? Each one of these atoms have this 1 valence electron. So that means there'll be a total of 2 valence electrons in molecular hydrogen, the hydrogen molecule. Awesome. Let's move on. Atoms are so boring. We're going to be studying molecules. So what is the simplest molecule? Because let's just get started talking about them. Yes, the simplest molecule is the one we were just discussing. It's the hydrogen molecule. It's the simplest because it's made up of 2 protons and 2 electrons. Let's draw the Lewis structure for the hydrogen molecule. Well, Lewis structures will show all valence electrons in all atoms. And we show the valence electrons because those are doing the bonding. The hydrogen molecule is made when 2 hydrogen atoms come together and share electrons. That is what covalent bonding is all about, right? Sharing electrons in between the 2 atoms. Whereas ionic bonding involves the transfer of electrons. Covalent bonding involves the sharing of electrons. Now we know that we will show shared electrons as lines. So how we will really draw the structure is like this, where the shared electrons are a line. We should recall that each line represents 2 shared electrons. Excellent. I've told you chemistry is all about the electrons. So can we describe the location and energy of the electrons in this molecule? Well, we can kind of describe the location, right? They're in between the 2 atoms. But what theory do we use to describe those electrons? Yes, we will use molecular orbital theory, and we'll discuss it more later. Now that we remember how to show the bonding in molecules, let's consider why atoms make bonds. What do you think? Common answers that I get from students are that atoms make bonds to get 8 valence electrons or to become stable. When we say an atom is acting to become stable, we mean it's going to lower energy. Well, why is it that these electrons end up lower energy in the hydrogen molecule? So bonding would not happen if this were not a downhill process. So these electrons are lower energy than where they started. Why? That's right. Chemistry is all about electrostatics. Think about what happens to the electrons. In the atoms, the electrons just experience one positive charge. But in the molecule, the electrons experience two positive charges. And we know from physics that the greater the magnitude of the charges, the stronger the attraction between them. Attractive forces or attractive energies are negative. So the stronger the attraction, the lower energy the electrons are. Chemistry is all about electrons, and electrons go to the lowest energy orbital. In fact, the entire universe is moving to lower energy spontaneously. Take a moment, pause the video, and list some low energy places for an electron to be. Let's compare. The absolute lowest energy atomic orbital is the 1s orbital. For a given energy level n, the s subshell will be lower energy than the p subshell when there's more than one electron. And I will quickly explain that. And if you don't want to hear the explanation, that's fine. You don't have to. This has to do with the nature of s versus p orbitals. There is a non-zero probability that an electron in an s orbital is actually on the nucleus. That is not, however, the case for an electron in a p orbital because p orbitals have nodes on the nucleus. So an electron in a p orbital can never be on the nucleus. Now, why does this matter? Well, the nucleus is the happy place for an electron. It's positively charged. The electron is negatively charged, and opposites attract. When there's more than one electron in an atom, the electrons in the s orbital, since they can be on the nucleus, when they are on the nucleus, they they decrease the attraction between the nucleus and an electron in a p orbital, because that electron on the p orbital, it can never be on the nucleus because of that node. And this is called shielding. Okay, and it explains why for a given energy shell, an electron in the s subshell will be lower energy than an electron in the p subshell. Finally, we've seen that sharing electrons lowers their energy. We saw in the hydrogen molecule, the electrons were lower energy than in the atom because they experienced two nuclei rather than one. So sharing electrons also lowers their energy. Let's think about those bonding electrons a little bit more. We'll start by defining terms. So pause and define in words and with diagrams the terms bond length and bond strength. Let's compare answers. Bond length is the distance between the two nuclei making the bond. Bond strength is the energy required to break the bond, to take those two atoms making a molecule and return them to just atoms. Take those electrons from being in between the two nuclei to just being around one nucleus. And because of that, it requires energy. You have to break up the attraction between the bonding electrons and the nuclei between which they are located. Let's now consider this question I've highlighted. Why does a particular bond have a defined length? For example, you may have learned in general chemistry that a carbon-carbon single bond has a characteristic bond length of 1.54 angstroms. Perhaps you did not learn angstroms. I will mention them quickly. They are a unit of length that corresponds to 10 to the negative 10 meters. In your textbook, you'll notice the more standard metric prefix used, picometers, which are 10 to the negative 12 meters. Why are carbon-carbon single bonds typically about 1.54 angstroms? Well, the answer is simple, right? It's because that length is going to represent the lowest energy for the electrons. Let's attempt to provide a physical basis for this. I will walk you through what I have drawn here at the bottom of the screen. So we're going to think about two carbon atoms, here they are, and we're going to consider the distance between the atoms. The distance between them is the bond length. We're going to start them out with a really big distance between them. They're so far apart right now. and so big values of R here on the x-axis. And we're going to imagine bringing those atoms closer together. And we will consider the energy of attraction or repulsion between the two atoms. Negative energy will be attractive. High energy represents repulsion. And then an energy of 0 means the atoms they're not attracted to each other, they're not repulsed by each other, they don't even know the other atom exists. So when we have a big distance here, so when R approaches infinity, those atoms don't know the other one exists. There's no attraction, there's no repulsion. The energy is about 0. Now, as R decreases and you bring these two atoms closer together, imagine they're coming closer together. Just draw that. Okay, so look, now they're closer. They begin to be attracted to one another. The electrons of one atom are attracted to the nucleus of the other. Keep getting them closer together. R is decreasing as I move to the left here. The energy of attraction increases, becoming more and more negative until all of a sudden, oh, they're too close. The nuclei repel, and they keep repelling. Oh, way too close, way too close. And as you approach the two atoms being on top of each other, there's a huge repulsion between the two nuclei. Now, this energy minimum, this maximum attraction between the two atoms, where the electrons of the atoms are maximally attracted to the nuclei of the other atoms and the repulsions are minimized, this represents the ideal bond length. And it's characteristic for a given set of nuclei and a given number of electrons. So two carbon atoms, when they are sharing just 2 electrons, this energy minimum is usually about 154 picometers. I'm sure you've seen a table similar to this one before of bond energies and bond lengths. I'm going to zoom into this table and ask you to take a look and describe any trends that you see in this data. Here you go. Take a minute. List any trends that you notice. What did you come up with? Consider the data in table 1-3. We have data for single bonds, double bonds, and triple bonds between atoms. We'll begin with the carbon-carbon data. So we see the single bond has that characteristic bond length of 154. Double bond getting a little bit shorter, 134 picometers. Triple bond even shorter, 120. As the bond length is decreasing, the bond strength is increasing. We can look at the data in kilojoules or kcals. Let's look at it in kcals. 81 kcals for the single bond, 148 kcals per mole for the double bond, 194 kcals per mole for the triple bond. So as the bonds are getting shorter, they are also getting stronger. Is that general? Is that a general trend? Can we give other examples of that phenomena in this data? Okay, you look, I'm going to write down our trend. Did you find any more examples of this? Sure, we could point out many examples, but we'll take a quick look here. We could look at carbon bonding with different halogens. All right, what's happening to the bond energies of the CF, CCl, CBr, Ci bonds? Yeah, they're getting weaker. The bond energies are decreasing. What's happening to the bond lengths? Yeah, they're getting larger. The data is not here, but you know that fluorine is smaller than chlorine, is smaller than bromine, is smaller than iodine, right? Atomic radius increases down a column. So iodine is the biggest among the halogens and fluorine is the smallest. Atomic radius increases down a column. So great, we see that as those carbon halogen bonds are getting longer, they are also getting weaker. If you saw any more trends, be sure that you write them down. Let's apply some of this knowledge. Rank the carbon-carbon bonds and these 3 molecules, so this bond, and this bond, from strongest to weakest, and then consider how do your rankings relate to the trends that we just identified. Among these 3 carbon-carbon bonds, The single bond with 2 shared electrons will represent the weakest bond. It will have the lowest bond energy. And the triple bond with 6 shared electrons will represent the strongest bond and will have the highest bond energy. These rankings relate directly to the trends we just identified, which are that shorter bonds are stronger bonds. We saw that as bond order increases, going from single to double to triple bond, the bond energy increases and the length decreases. Shorter and stronger bonds. It comes as no surprise to us that the longest bond is the carbon-carbon single bond with a characteristic bond length of about 1.54 angstroms, or I'm sorry, I can't stop myself from using angstroms, or 154 picometers. And then the shortest bond is the triple bond. So we're not surprised about that. We just said that. But can we provide a microscopic explanation for this phenomena? All right, you try to do that right now. The key lies in the number of electrons shared in each of these bonds. The single bond has 2 shared electrons, the double bond represents 4 shared electrons, and the triple bond 6 shared electrons. I have referred to Coulomb's law a couple times today, but I haven't explicitly written it out. The attraction or repulsion between two charged bodies is constant K times the charge of particle 1 times the charge of particle 2 divided by the distance between the two particles squared. What does that have to do with this? Well, the electrons are the charged particles, and you can see that their charge is increasing. We have a charge of 2, -4, -6. And so the bigger this charge gets, and the nuclei aren't changing, right? The nuclei, the carbon nuclei, those represent the first charged particle. The number of protons isn't changing, but the number of electrons is, and so the total charge is changing. And the bigger that charge is, the more electrons there are, the bigger the attractive force, pulling those nuclei together, resulting in a stronger, shorter bond. I have good news. We have met our first learning goal, which is to describe the bonding in organic compounds, including trends in bond length and bond strength. So let's move on. Let's anchor our discussion in this question, why do atoms make bonds? So what did we say previously? Common answers I hear are to be stable, and usually that means to get 8 valence electrons around all the atoms in the molecule. Again, this is often, it is not always. There are very few always statements in chemistry. And if it's an always statement, there's probably law in front of the name. And this is not the octet law, it is the octet rule, octet observation, etc. So how will we represent these bonds? Well, we'll start by drawing complete Lewis structures. Take a moment and jot down your answer to this question if you have not done so already. What is a Lewis structure? What do you remember from general chemistry? A complete Lewis structure shows all valence electrons and atoms. Why the valence electrons? Well, these are the highest energy electrons. They're reacting, they're making bonds to become more stable, and so that the entire system is at lower energy after the bonds are formed. There are 2 types of electrons in Lewis structures. They are the bonding electrons and non-bonding electrons. We represent bonding electrons as lines, just like we showed for the hydrogen molecule in the beginning of our discussion. Non-bonding electrons are represented as dots or as lone pairs of electrons. For example, in ammonia, there is a lone pair of electrons on nitrogen. There are bonding electrons and non-bonding electrons. NB, non-bonding. And finally, most atoms bond to achieve an octet, which corresponds to 8 valence electrons. For example, the nitrogen in ammonia has 2, 4, 6, 8 electrons around it as a result of bonding with 3 hydrogen atoms. Most atoms bond to achieve an octet, but not all. Let's pause for a moment and look at some exceptions to the octet rule. Now, the octet rule refers to 8 valence electrons, a noble gas electron configuration where the entire S and P subshells are filled. There are 3 common exceptions to the octet rule with which you should be familiar. Let's start with fewer than 8 electrons, so not quite an octet. The example that you're probably familiar with is BH3, borane. So boron often just has 6 valence electrons around it. Atoms might have more than 8 valence electrons around them. Examples with which you might be familiar would be sulfur hexachloride, phosphorus hexachloride. Sulfur and phosphorus are in the 3rd row of the periodic table. And that means they have what? They have d orbitals. They have a d subshell. Anything past the 2nd row will have a d subshell. And thus, instead of just having 4 orbitals with which to make bonds, right? The s and the p's, 4 orbitals, 2 electrons per orbital, 8 electrons, octet. They have more orbitals. They have the d orbitals, and so they can make more bonds. Now, I'll let you know something. You will see carbon with fewer than 8 electrons sometimes. You will not see carbon with more than 8 electrons. Why not? Carbon's valence shell is shell 2, which only contains the s and p subshells, 4 orbitals with which to make 4 bonds and accommodate 8 total electrons. There's one last exception to the octet rule that we will examine, which is an odd number of electrons. We will encounter these examples more rarely. We can look right now, though, at NO. Its Lewis structure would look like this, where we can see we have an odd number of electrons. We have this unpaired electrons. Species with unpaired electrons are called radicals, and we will discuss the chemistry of organic radicals later in the semester. We've gotten warmed up thinking about exceptions to the octet rule. Let's move on and continue warming up. Let's think about patterns in covalent bonding. It will be much easier for you to draw and analyze Lewis structures if you're familiar with the patterns in covalent bonding. Please pause and see if you can fill this table out yourself. I'll give you an example though. Neon has 8 valence electrons. Its electron dot symbol looks a bit like this, putting those 8 valence electrons around it. Because neon already has 8 electrons, it doesn't typically make covalent bonds, and it has 4 lone pairs. 1, 2, 3, 4. Example compounds, well, neon doesn't make any compounds. All right, your turn. Yours will be harder. Ready, set, go. Your answer should look a bit like this, where group number corresponds to the number of valence electrons in the atom. Number of valence electrons tells you how many dots you'll have in your electron dot symbol. Because carbon has 4 valence electrons, it needs 4 more. Needs 4 more to do what? To have a complete octet. So if it needs 4 more, it makes 4 bonds. With those 4 bonds, carbon has 8 valence electrons around it. 2, 4, 6, 8. Or, an example on the right, 2, 4, 6, 8. Carbon does not typically have any lone pairs on it, typically, but it can. And we'll see examples of that today. Nitrogen is in group 5A, so it has 5 valence electrons, which we can show like this. It makes 3 bonds because 5 plus 3 is 8. And then you'll have 1 pair of electrons left over. There it is. This is the usual bonding pattern for nitrogen, but we will see deviations from this. This is just the usual lowest energy patterns for bonding, but we will be addressing high energy species in our class and they will deviate from these patterns. But this is a good starting place. All right, I hope that jogged your memory. Finish reviewing this slide and then move on. Let's move on to listing some strategies for drawing Lewis structures. So I want you to list your strategies here right now. I would guess that some of you maybe wrote that you write the atoms out and then sort of make them have octets. This type of strategy will not work this term because, like I said, not everything is going to have an octet because we're going to be examining low energy, high energy, and not everything is going to follow its usual patterns. So we should know the usual patterns, and you'll see why in a minute, but our strategy should not be just kind of make them have octets or make the atoms have the right number of bonds. That will not be the best place to start because, again, we will see deviations from this. I have given you what I call Lewis structure rules, and these are really guidelines, and I would like for you to have them out next to you while you are practicing Lewis structures today. Where we start is by counting the total number of valence electrons that should appear in the structure, and that's because valence electrons do bonding. Now, step 2 is the hard part. Arrange the atoms in the correct arrangement. Cool, it's that easy, right? Yeah, I mean, with practice. So I'll show you some examples of this. Often we'll encounter structural formulas that indicate the ways that the atoms should be bonded to one another. For example, we'll see in this molecular formula in a little bit, and this is telling you these 3 hydrogens are bonded to carbon. So use the formula as a clue. Often the least electronegative atom or the atom that makes the most bonds will be in the middle. So just recall central atoms are bond to more than one atom, and then terminal atoms bond to just one atom. So in this example, A is the central atom and B is a terminal atom. And so for example, if you were trying to decide what should be the central atom, should it be carbon or fluorine? Well, it should be carbon because carbon makes more bonds than fluorine. Excellent. So you're going to review the rest of these rules by yourself or just have them next to you, and then we're going to practice using them right now. All right, do it my way. So I want you to use the guidelines on the Lewis structure rules handout to draw complete Lewis structures for each of these compounds. I'll do one for you now. If you'd rather try them yourself first, then just stop the video now. I'll try PF3. So first I'm going to count the valence electrons. Phosphorus is in group 5A. It has 5 valence electrons. We have 3 fluorines, and each fluorine atom has 7 valence electrons because they are in group 7A. This gives me a total of 26 valence electrons that will appear in the structure. Step 2, arrange the atoms in the proper arrangement. Well, phosphorus is in group 5A, so it typically makes 3 bonds. Thus, I'm going to make it the central atom because fluorine only makes 1 bond. Also, fluorine is more electronegative than phosphorus. So either way you want to look at it here, we're going to put phosphorus in the middle. Now we stop and we count electrons because we might be done with the structure. But right now we only have 2, 4, 6 electrons, and we're supposed to have 26. So your next step tells you to fill the octets of the terminal atoms. The terminal atoms are the fluorine atoms, and before I started drawing the lone pairs, they only had the 2 electrons from the bond. So I'm adding 6 more. Now we stop and count. If we stop and count now, which you should do, we'll have 24 electrons. We're not supposed to have 24, we're supposed to have 26. So we need to do something with those 2 additional electrons, And our guidelines tell us to put them on the central atom, which is phosphorus. Now we stop and we count. We need to do some checking. We first need to check our total valence electrons. This must always be true. If our structure doesn't have the right number of valence electrons, then we have drawn it incorrectly. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is a check. Super. What should we check next? Yes, now the next two checks are just going to be usuallys. So we're going to check octets and we're going to check the usual number of bonds and lone pairs. So these are going to be usuallys. They're not always. The only always is total number of valence electrons. But all these atoms do have octets. We'll start with one of the fluorine atoms. So 2, 4, 6, 8. Phosphorus, 2, 4, 6, 8. Good. So total valence electrons check, octets check, and then finally usual number of bonds and lone pairs. That's coming from the patterns that we came up with together. Phosphorus, being in group 5A, will behave like nitrogen, typically making 3 bonds with 1 lone pair. Fluorine, we expect to make 1 bond with 3 lone pairs. Let's check. That is indeed what both atoms are doing, so this is also a check. If any of these things are not a check, then you need to just review your structure and make sure that you didn't miss anything. But again, the only one that always needs to add up are the total number of valence electrons. Awesome, so you should try these yourself and then we'll do a few more together. Now that you've tried these on your own, let's do a few more together. Let's try this one, H2O2, hydrogen peroxide. Don't skip the first step, which is to count the total number of valence electrons. Each hydrogen atom has 1 valence electron, and there are 2 of them. Each oxygen atom has 6 valence electrons, and there are 2 of them. This gives us a total of 14 electrons in the structure. Hydrogen can only be a terminal atom. It can only make 1 bond. So really we have 2 choices here. We can connect all the atoms in a line, or each oxygen has 1 hydrogen atom around it, or on step 2 and step 3, arrange the atoms and connect them with a single line. Or we could try something like this. Now I see this quite frequently in class. Why is this not the right structure? So I'm not even going to continue through the putting in a lone pair, so you could if you want, but how can we recognize that's not the right structure? Yeah, the way to recognize it is because the oxygen on the left is making 3 bonds, and it typically makes 2. The oxygen on the right is making 1 bond, and oxygen typically makes 2. And the other way of arranging the atoms has 2 bonds per oxygen. So if we can do it this way, and we can get the correct total number of valence electrons, then this, circled in pink this way, with each oxygen bonding to 1 hydrogen, that will be preferred. So let's try that. Let's see if we can make it work with that arrangement of the atoms. Now we need to fill the octets of terminal atoms. Of course, the terminal atoms are hydrogen. They do not get an octet, they get a duet. So we need to add the remaining electrons, which would be how many? Well, there's 2, 4, 6. We're supposed to have 14. So there are 8 additional electrons. We need to add them to the oxygens, and we're going to add 4 to each oxygen. So at this point, there are 14 total electrons in the structure. Both oxygens have octets and hydrogen has its duet. I will count for the oxygen on the left. 2, 4, 6, 8. Each oxygen is making its usual number of bonds and lone pairs. Oxygen and group 6A elements usually make 2 bonds, 1, 2, and have 2 lone pairs, 1, 2. So each oxygen is doing that. And again, that is how we knew the alternative arrangement of atoms was not going to lead us to a productive structure, because both oxygens are not making the usual number of bonds, and they can if you just arrange them this way. So I'm happy with our structure, and let's move on. Let's try formaldehyde, CH2O. 4 valence electrons from carbon, 1 from each hydrogen, 6 from oxygen. Again, using those group numbers. 12 total electrons will appear in this structure. Now, what should be the central atom? Should it be carbon or oxygen? It should be carbon. Now, I'll go ahead and I'll draw the wrong arrangement of atoms first. So sometimes I see that. Now, how do we know that's not going to be correct? Well, several ways. We could bring this forward in several different ways. But one of the atoms, carbon or oxygen, it's not going to make much sense. So we could draw, okay, there we go. Now we have 4 bonds to carbon. Well, what in the world is oxygen doing? It doesn't make 4 bonds. Okay, let's put lone pairs on it. Well, now let's violate the octet rule. So in this arrangement of atoms, we will not be able to draw a structure that is consistent with our chemical intuition, which we all have. It involves these patterns that we're making explicit, by making, for example, this table. And your chemical intuition also includes all the hundreds of Lewis structures that I'm sure you diligently drew in Chem 1A. So because oxygen makes 4 bonds, all 3 of these atoms can be accommodated around it. Connecting atoms with a single line. Right, now from here, you might know what to do. You might instinctively say, all right, carbon makes 1 more bond, and then oxygen is going to have 2 bonds now, and it has 2 lone pairs. That's fine. If you can instinctually do that with your chemical intuition, I'm perfectly happy with that. Let's check it, and then I'll show you how to get there if you don't have those instincts yet, which again, that's fine. We're all developing at our own pace. So let's check the total number of valence electrons. We're supposed to have 12. There's 2, 4, 6, 8, 10, 12. Yes. Check on the total valence electrons. Let's check octets. Carbon, 2, 4, 6, 8. Awesome. Oxygen, yes, 2, 4, 6, 8. So octets are a check. And then we've already discussed the usual number of bonds. Oxygen is making 2 bonds. There are 2 lines and 2 lone pairs. Carbon is making 4 bonds, 4 lines. So they're both making their usual number of bonds to achieve complete octets. So I feel pretty good about that structure. Now I said I would show you how to get there if you couldn't quite, if your instincts weren't quite leading you there yet immediately. Now, after we drew the atoms in the proper arrangement, step 2, we connected each pair of adjacent atoms with a single bond. We need to complete the octets of terminal atoms. So we'll do that. So oxygen was the terminal atom, and if we complete its octet, that requires 6 electrons. Now when we get here, we stop and count, and we have 2, 4, 6, 8, 10, 12 electrons. And that's it for this structure. That's it. There are no more electrons. I know that from our initial count. And I can see carbon doesn't have an octet yet, and it's not making its usual number of bonds. It needs 1 more bond, right? You might also notice, hey, look at oxygen. It's only making 1 bond and it has 3 lone pairs. It should only have 2 lone pairs. So what do? Yeah, you share one of those lone pairs. So we'll take this lone pair, and instead of having it on oxygen, we just share it. And guess what? That gets us right here. That gets us right to the actual structure. I'm going to project the answers to the rest of the problems. You should pause and just check your answers. And when you're ready, let's take a look at this ion. So there's something that you'll notice. You'll notice that this carbon atom that I'll make in pink here, it does not have an octet. And so you might say, is that legal? Yes, that is legal. We will encounter this ion in our class. And that's why there's a formal charge. So see, there's a positive formal charge on carbon here. So there's a formal charge because carbon is not making its usual number of bonds, and it has an incomplete octet. You see the same thing over here for the acetate ion. And the acetate ion, I've indicated a negative charge on this oxygen that is not making its usual number of bonds. It has 3 lone pairs and 1 bond. Both of these cases, these are the right structures. And I know that because there's no better alternative, and because when I did my total valence electron count, the structure meets it. So let's see, we have 4 carbon atoms. Each one has 4 valence electrons. There are 9 hydrogen atoms. Each one has 1 valence electron. So we should have a total of valence electrons in this structure of 25. No, right? No. Wait, hold up, hold it up. Because you have to subtract the 1 electron from the positive 1 charge. So the positive 1 charge means 1 fewer electron. So it's lost an electron. Good, so 24 total electrons should be in our structure. And we have 24, I'll count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And all the other carbon and hydrogen atoms are making their usual number of bonds. And all the other atoms have octets. It's just that central atom that doesn't. So we have correctly drawn the structure. And why the central atom with an incomplete octet? Well, because that's what the formula tells us. The formula tells us that that central atom, which I have in pink, has 3 CH3 groups around it. And that's what we have here. So I'm confident that we drew that structure correctly. I will point out one more thing. During the total electron count for the acetate ion, there is a negative formal charge, so I would add 1 electron to the valence electron count, because that's what the negative charge means. And don't worry, do not worry, that is written out for you somewhere. It's written out for you right here. Be sure to account for the extra or fewer electrons in a polyatomic ion. You're going to subtract electrons when there's a positive charge, and you're going to add electrons when there is a negative charge. Do not worry if you didn't get all of these right the first time. Don't worry at all about that, actually, because you're not going to get them all right the first time. Nobody does. And that's okay. This is going to take lots and lots of practice. It requires practice to build up your chemical intuition so that you can draw structures quickly and get a sense of what looks right and what looks wrong. What's important right now is that you know how to evaluate your work. So pause and write down how you evaluate your Lewis structure to check if it's correct. Always, the total number of valence electrons in the formula should match that in the structure. And then usually all atoms have octets that are supposed to have them, and atoms are making their usual number of bonds. And just remember to look for clues. We have clues in the formulas. There was a clue in this formula. There's a clue in this formula. There's a clue in this formula. Look, CH3. It tells you there should be a CH3 here. So look for your clues and trust yourself. So again, it's okay to be wrong the first time. Learn how to revise. Good talk. Let's revisit this idea of formal charge. So we saw carbon had a positive formal charge on it and the tert-butyl cation, that's the name of that ion. And in acetate, we had a formal charge on oxygen. One of your goals today is to draw Lewis structures with the correct formal charge. When an atom isn't bonding, in other words, sharing electrons, in its ideal way, it probably has a formal charge, just as we saw for acetate and the tert-butyl cation. We'll look at a simpler example. Oxygen usually makes 2 bonds and has 2 lone pairs, as it does in water. However, you are probably pretty familiar with 2 ions related to water. The first of those is hydroxide, and the second of those ions is the hydronium ion. For the oxygen in hydroxide, we can see that it is more electron rich than is usual, or than is lowest energy for oxygen. And what I mean by that is that there are 3 lone pairs and 1 bonding pair of electrons. And typically oxygen shares more, but not in hydroxide. In hydroxide, instead of sharing this lone pair, it's localized on oxygen. So oxygen has more electrons than usual, and so it has a negative formal charge. That oxygen in hydroxide is more electron rich than is ideal. On the contrary, the oxygen in hydronium is less electron rich than is ideal because it only has 1 lone pair, 1 pair of non-bonding electrons, and 3 bonding pairs. So it's sharing more than usual, and that makes it less electron rich. It's sharing these electrons instead of having them as a lone pair localized on that oxygen atom. And hydronium will behave in a way to regain the electrons that are being shared here. As you know, that's why it acts as an acid. You will recognize that atoms have formal charge with practice and by looking for patterns. When an atom doesn't have its usual number of bonds and lone pairs, it probably has a formal charge, and you should stop and check. This underscores, once again, the importance of familiarizing yourself with the regular patterns in covalent bonding that we've been discussing. Now that you know what to look for, how do you calculate a formal charge? Well, this is the formula that I use. Take the number of valence electrons for a neutral atom. So for these examples, we can see that it's oxygen that isn't behaving in its normal way. It's not bonding in its usual lowest energy fashion. So you'd want the number of valence electrons for a neutral atom of oxygen. And I'll do an example in a moment. And then subtract from that the total number of lines plus dots. So basically you count each individual electron of a lone pair. So you count the lone pair twice. And that gives you the formal charge for that particular atom. No worries if you have no clue what I'm talking about. I probably am not making sense. Let's look at an example. So for the oxygen and hydroxide, a neutral oxygen atom has 6 valence electrons because it is in group 6A. This oxygen atom, remember total number of lines and dots, has 1 line, and then 2, 3, 4, 5, 6, 7. So 7 total lines plus dots. Again, like I said, we're counting the lone pairs twice, basically. Since they're localized, each electron is localized on oxygen. It's not being shared with hydrogen. 6 minus -7 gives us -1. That is the formal charge of the oxygen atom in hydroxide. As we do, typically we ignore the 1, but you could have written -1, but the 1 is implied. We don't ignore it, we imply it. All right, for the oxygen and hydronium, same deal. 6 is the number of valence electrons for a neutral oxygen atom. And then count the lines plus dots. 1, 2, 3, 4, 5. 6 minus 5, +1. That is the formal charge on that oxygen atom. And again, the 1 was implied. You'll have some time to practice with this. I would like for you to draw the complete Lewis structures for each of these compounds, including all atoms, bonds, lone pairs, and formal charges. I'm not going to go through the Lewis structures, so if you have questions about them, ask me. But I want you to stop, draw the Lewis structures, and really try this, and then come back and compare with me. For nitromethane, we see that 2 atoms, nitrogen and this oxygen, are not making their usual number of bonds and lone pairs. Nitrogen usually makes 3 bonds with 1 lone pair. A neutral atom has 5 valence electrons. Subtract 4 lines, no dots, gives us +1, and that is the formal charge of that nitrogen atom. Oxygen usually makes 2 bonds with 2 lone pairs. We see that is not happening here. 6 valence electrons for a neutral oxygen atom minus 7 lines plus dots, 1, 2, 3, 4, 5, 6, 7, gives us a -1 formal charge for that oxygen atom. Carbon, again, usually makes 4 bonds. It's not doing that. So -4 minus 5, 4 because that's the number of valence electrons for a neutral atom, and 5 because that's the number of lines plus dots. So 1, 2, 3, 4, 5. So -1 formal charge for that carbon atom. Nitrogen, too many electrons, right? Usually has 3 bonds and 1 lone pair. So 5 minus 6 gives us -1. 5 is the number of valence electrons for a neutral atom. 6 is the number of lines plus dots. Nitrogen atom in ammonium. It has a formal charge of +1. A neutral atom has 5 valence electrons minus 4 lines, gives us +1 for the formal charge. Let's summarize. I actually suggest you fill this chart in on your own. So the number of bonds and lone pairs for zero formal charge, that's from the table we did earlier. And then what might you encounter for a positive formal charge? What might you encounter for a negative formal charge? So at a minimum, pause and think. And I'm going to switch to the answers pretty quickly here. Last chance. So there is too much sharing or an incomplete octet when there's a positive formal charge. There is less sharing than normal, or more lone pairs, I suppose we could say, when we have a negative formal charge. Negative formal charge suggests that the atom is electron rich. Okay, so here you go. Take a look at this. I'm not going to go through all of it, but let me know if you have questions. So pause and think about it. Now that we can think about these patterns, what sorts of predictions can we make? So when we see a positive formal charge in a molecule, what do you think that molecule will do? Or what will the atom do that has that positive formal charge? And obviously, or not obviously, I'm abbreviating formal charge as FC, not football club, formal charge. Yeah, if a molecule or an atom has a positive formal charge, it's probably going to react to get electrons. And if a molecule or atom has a negative formal charge, it's probably going to react to give up or donate electrons. So you want to keep that in mind, and that's part of why it's just so important that you can recognize formal charge in molecules. Last topic. So we need to be able to draw resonance structures. So we're going to try that with the formate ion. So here is the molecular formula of the formate ion. I would like for you to pause and draw the complete Lewis structure. I also want you to predict the bond lengths for all the bonds. So the way that you'll do that is to go back to this table right here and look at the bond lengths. So you have CO, single bonds, double bonds. So this data will be important. CH, well, you don't have bond lengths for that. So just do it for the carbon-oxygen bonds. Try this problem. This would be a reasonable Lewis structure for the formate ion. Let's now try to predict those bond lengths. And we will use the data that we discussed previously in this video. I know, it was a long time ago. We're almost done, I promise. We'll use this data to analyze the structure. Now, if this carbon-oxygen bond is a double bond, then we would predict a bond length, probably close to 1.2 angstroms. That's what I'm getting from the data, or 120 picometers if you rather. If this carbon-oxygen bond is as drawn, a single bond, then we will predict a bond length of about 1.43 angstroms, as is indicated in this table, which we have no reason to doubt. Now let's go ahead and compare our predictions with the data. So if there is data we can get, people grow crystals, like a crystal of sugar or a crystal of salt. They grow crystals of compounds. For the technique of X-ray crystallography, they can measure the distance between the nuclei. So I got this data from the Cambridge Crystallographic Data Center. And it turns out that this carbon-oxygen bond number 1 and carbon-oxygen bond number 2 have a pretty similar bond length of about 1.23 angstroms. So those two bonds have a similar bond length. So we were pretty close on, no, not that one. We were pretty close on this bond, but we were way off on this bond. So what is going on? What are we missing? Are you yelling at the screen? Yeah, what is to say that it has to be oxygen number 1 that makes the double bond to carbon? Why can't oxygen number 2 make the double bond to carbon? Well, it can, and apparently it does. Apparently, both of these oxygens are making some sort of double bonding interaction with carbon because both of the bonds have the same exact bond length, which is really close to that of a carbon-oxygen double bond. Well, we overlooked the fact that this molecule, the formate ion, is described by resonance structures. So in light of that information, what is the best way to represent the formate ion and to explain the fact that the two carbon-oxygen bond lengths are exactly the same? Okay, write down your best explanation. I know I'm writing something else while I'm talking to you. Write down your best explanation. Pause and do that, and then come back and listen to my explanation. The formate ion is a composite of both of these resonance structures. In fact, both of the oxygen atoms make some sort of double bonding, some sort of pi bonding interaction with the carbon atom at the same time. Both of these oxygens share that positive formal charge. And so we can actually show the electrons from the pi bond spread out. Or if you don't remember pi bonds, those electrons in the double bond, we can show them spread out over all three atoms. And that explains why both of the CO bonds have the same bond length, and those CO bonds are just a little bit longer than a typical carbon-oxygen double bond. Let's make sure that we remember resonance structures, what they are and how to draw them, and when to recognize that we should be considering them. Resonance structures are different arrangements of valence electrons. You do not move any atoms. It's just different arrangements of the valence electrons. The real electronic structure of a molecule that is described by resonance structures is a composite, a combination of the two resonance structures, or the however many you can, of all the resonance structures that you can draw. And it might not be an equal composite. There can be major and minor resonance structures, but the real molecule is a composite of the resonance structures. Just like we saw for the example of formate. Formate is best described as this composite, this combination of these two resonance structures. And that's indicated by the carbon-oxygen bonds having the same length. Each of the molecules in this table can be described by a resonance structure. I would like for you to pause and draw those resonance structures and then describe the pattern that we may be able to look for later for other molecules that can also be described by resonance structures. So please pause and try this. I know you're tired, I am too. Pause and try. Here are the resonance structures for each of these molecules. I shall point out one thing before we get started discussing the resonance structures. This arrow here, this means one thing and one thing only. This indicates that two structures are resonance structures. It is possible that you have seen that arrow used to indicate equilibrium in a previous class. That is not what this arrow means. This arrow means that two things are resonance structures, and resonance structures are not in equilibrium. They both exist at the same time. There are two different ways to represent the same molecule because those structures aren't perfect. All right, so this arrow means one thing and one thing only. It means two drawings are resonance structures of one another. Neither one of them exists. The real molecule is a composite of them. Excellent. So for benzene, the first molecule here, we could have drawn the pi bonds, just shifted over. And I'm going to use the curved arrow formalism to indicate how the electrons can be thought to move to convert between the two resonance structures. So arrows start at the electrons and they point to where they're going. In the allyl cation, that is the second molecule here, we could have drawn the double bond between these two carbons. We'll number them. We could have drawn the double bond between carbons 1 and 2 rather than between carbons 2 and 3. Why not? They're the same, right? Okay. In our next example, we'll look down here in the bottom left. This is the allyl anion. we could have drawn this lone pair of electrons actually being shared and a lone pair on this carbon. So let's number our carbons. This time carbon 3 could be the anion. Why not, right? There's no reason not to show this structure. So it's a different arrangement of the valence electrons. I haven't moved any atoms. I haven't violated any rules. And the real structure of the allyl anion is a combination of these two. Here's formaldehyde again, and this would be one way to draw formaldehyde. Some of you may have when we drew the Lewis structures of it. But why can't I share these electrons and form a pi bond? I probably should, right? This is how you would usually draw the molecule. All right, these all represent resonance structures, and I chose each of these examples to represent a pattern that you should keep your eyes out for. First pattern, adjacent double bonds or adjacent pi bonds. When you have two double bonds, or more than two in this case, next to each other, adjacent, you can probably draw a resonance structure. Second pattern, a double bond adjacent to an empty orbital. Here's a double bond. You might say, well, how do I know there's an empty orbital there? Well, you will very shortly review this with me, but you should hopefully remember from Gen Chem that there's an empty orbital there. There's an unfilled octet, right? But we'll get there. We'll review that next. Not today, don't worry. Third pattern, lone pair adjacent to a pi bond or to a double bond. Then you can probably draw a resonance structure. Fourth pattern, lone pair adjacent to an empty orbital. So here's the lone pair, here's the empty orbital, and we drew the double bond. All right, so those are your 4 patterns. I know, you need more time than that, but you'll have more time. You're going to study, so write down the patterns, think about them, keep them in mind when you're doing practice problems. So you're going to want to recognize them. Now, just because the real molecule is a composite of the 2 resonance structures, right? So I said all of these molecules are actually composites, just like we said for the formate ion. It's best described as a 50-50 mixture of these 2 resonance structures because they are equivalent to one another. There's no difference. That's not always the case. So we do need to know how to determine how each resonance structure contributes to the overall electronic structure of the molecule. So we need to figure out which is the major resonance structure, which is the most stable, for example. Which resonance structure maybe is a little less stable, maybe contributes less to the electronic structure of the molecule. Or there's a situation where the 2 resonance structures might be exactly equivalent. You can't tell them apart, like in the case of the formate ion. And then you're going to have a 50-50 mixture of the 2 resonance structures. Or if there's 3 equivalent resonance structures, then it's a 33.3, 33.3, 33.3. Fun. Contribution of each resonance structure. I have 3 examples here, and these are very carefully chosen. So see if you can decide which of these resonance structures is the major or most contributing for each of these molecules, or if the 2 resonance structures are equivalent. For this first molecule, the allyl anion, we have 2 equivalent resonance structures. You cannot tell them apart. There is a C- or carbon ion adjacent to a pi bond to a CH-CH2. Same thing here, C- adjacent to a CH-CH2. If I spun these molecules around in space, you would not be able to tell them apart. So we have 2 equivalent resonance structures, which means that the actual electronic structure, the actual molecule, is a 50-50 mixture of these 2 structures. Means that these 2 bond lengths will actually be exactly the same, just like the CO bonds were for the formate ion. For molecule 2, this would not be the case, right? So the difference between these 2 resonance structures is a negative formal charge on oxygen, so oxygen having more electrons, versus on carbon. And in this case, this first structure would be the major resonance structure, and the structure with the carbon ion would be the minor resonance structure. And that's because the negative formal charge will be more stable on a more electronegative atom. So that molecule will look more like the major resonance structure. But it still is a composite, it just looks more like the major resonance structure. Now, our last example is a little more complicated, and if you got this one wrong, you should not feel bad because it is more challenging. The difference between these two resonance structures is a positive formal charge on carbon and a positive formal charge on oxygen. So that's one thing, right? So the positive formal charge on carbon versus the positive formal charge on oxygen. And like obviously that's going to be better on carbon because carbon is less electronegative than oxygen. But there's this second issue. And the first resonance structure, there's an incomplete octet on carbon. And in the second resonance structure, there are full octets on all atoms. So we have to decide what is more important. Is formal charge more important, or are all the atoms having filled octets more important? So what do you think? So we're going to prioritize octets over having the formal charge on the best atom based on electronegativity. So we're going to prioritize octets over formal charge, and we're going to do that because I looked at a lot of data and you get the answers right if you prioritize octets. So this is the major resonance structure because it has full octets on all atoms. Yes, oxygen has a positive formal charge. Turns out octets are more important. And I can explain to you why if you would like. I'd be happy to. You're going to have to send me an email. Okay, so that means that this molecule looks more like that structure, the full octets, versus the structure on the left. Spend some time thinking about this, and we'll work on it in our problem-solving sessions as well. All right, we're wrapping up. So how will you recognize when an atom has a formal charge? It will deviate from the usual number of bonds and lone pairs that it makes based on the number of valence electrons that the neutral atom has. So that table we made like a million minutes ago. For example, oxygen usually makes 2 bonds and has 2 lone pairs, but in hydroxide and in hydronium, oxygen is not doing that. It has fewer or more lone pairs than usual, and it has a formal charge in both of these molecules. All right, how will you recognize when an atom or molecule should be represented by more than one resonance structure? Well, those are the 4 patterns that we just discussed. So 2 really important tables today. We have this table, the patterns that you're going to fill in yourself from these examples. And we have our formal charge table, but really this one's not quite as important as just recognizing the normal patterns or the normal patterns of bonds and lone pairs. Because you really don't have to memorize this one. It's just a thought exercise because you know how to calculate formal charge now, or you will after you study. And then finally, what are the implications of formal charge in a molecule? Well, we were able to think about predicting how it reacts. If it's electron rich, it's going to react to donate electrons. If it's electron poor, because it has a positive formal charge, it might react to gain electrons. And then resonance structures, this has all kind of implications, but we saw that it had implications on the bond lengths. And I said the formal charges might be shared. So regions of electron density are also affected. I'm going to let you revisit the learning goals on your own. Make sure that you can do all of these things. But don't skip this step. You can do it yourself. And then again, you always need to summarize and reflect. This is a cumulative class and it relates to other classes that you're taking. That's why it's a requirement for you. So work through these questions and ask me what questions you have. Okay, time to practice. This is a really important one. Even if everything feels familiar from Gen Chem, you still need to practice.